In the last lesson, we introduced exponential functions and examined some basic laws of exponents. Today, we are going to extend those ideas to graphing such functions and exploring various transformations. Before we get there, however, I would like to briefly review some fundamentals. Seen here is the basic form of an exponential function, where x is the independent variable and y is the dependent variable. X is the input, y is the output. A is the scale factor. We saw this last time but didn't use it much. Today we will. Basically, the scale factor will either stretch or shrink the graph in the vertical direction. B is the base. If you want more details on that, please refer to the previous lesson, in which we discussed it more extensively. Let us begin with the function y equals 2 to the x. A equals 1 and b equals 2. Pulling this from the last lesson, we can produce the data table on the left and plot the points as so. Notice the scale on the y-axis ends at 1024, seen in orange, and the x values range from 1 to 10, seen in green. Now that we have a better understanding of the laws of exponents, we are going to employ them to extend our graph. Specifically, we are going to use the two laws boxed in red. Any number raised to the 0th power is 1, so 2 to the 0 is 1. 2 to the negative power is simply 1 divided by 2 to the same power, but positive. Those computations are shown here and expressed both in fraction and decimal format. Pause the video if you need a moment to digest this. Here I have tabulated the data on the left and plotted it on the right. Instead of x from 1 to 10, we now have x from -4 to +5. 10 data points in each case. The curve looks strikingly similar to what we saw before. However, notice in orange that the maximum y value is now 32 instead of 1024. If we were to disregard the numbers on the axis, we could actually overlay this curve on the previous one and it would match exactly. Interesting. Do note, however, that the position of the y-axis makes it appear as though the blue curve has shifted 5 units to the left. So now let's talk about translations. These rules apply to any function in general. Translations maintain the size and shape of a function. They just move it left, right, up, or down. In our example, we're going to be translating leftward, so we will use f of x plus h, as boxed in red. Using this law of exponents, we will see a curious connection. Shifting the function 5 units to the left looks like this. We can manipulate the sum in the exponent to be the product of two different exponentials. But 2 to the 5th is a constant, 32. So it appears that translating the exponential function to the left is the same as multiplying it by a constant value. This brings us to another category of transformations, dilations. For dilations in the vertical direction, if a is greater than 1, this results in stretching. A less than 1 results in squishing. The opposite can be said if we are talking about stretching or shrinking in the horizontal direction. Our case falls into a vertical stretch, as boxed in red. While on the note of function transformations, I should mention reflections. These can be achieved by including a negative sign in the appropriate location. This is simple enough. For a more complete set of transformations, I should also include rotations. However, this is an involved topic that is better reserved for a separate lesson. So let's get back to the main point. Here I have tabulated data from x equals -4 to x equals 5 and plotted it. This is for the function y equals 2 to the x plus 5, which is the same as y equals 32 times 2 to the x. Notice in green that the x values range from -4 to 5, like the second graph we saw. However, the scale on the y-axis reaches 1024, as seen in orange. This scale was seen on the first graph we saw. Focusing attention on the numbers instead of the graph, we see that each value in the third column is that of the first column minus 5. That corresponds to a leftward shift of 5 units. For the data points that are the same on the first two graphs, we can see that each input x, in pink, spits out the same output y, in red. Now to compare the data tables of the second and third graphs we saw. The x values are identical. However, the values boxed in orange are those boxed in blue multiplied by 32. Thus, numerically, we can see that a horizontal translation is equivalent to a dilation. For perspective, this is the first graph we saw. I have highlighted 5 data points in red. On the second graph we saw, these red dots are the exact same data points. It appears as though they have moved from one side of the same curve to the other. In reality, the illusion is due to how I have scaled the y-axis. In each case, the graph is the same height regardless of the maximum value. But it is interesting how the curve looks the same at different scales if we keep extending it. This is not the case for most functions. Enough of that. Let's look at a function with a different base. Y equals 3 to the x. Pulled from the last lesson, here's the data table and plot for x equals 1 to x equals 10. Notice the y-axis has a maximum value of 59,049. Employing laws of exponents, we can extend our plot to the negative numbers. Any number to the 0th power is 1, so 3 to the 0 equals 1. 3 to a negative exponent is 1 divided by 3 to that same exponent, positive. The computations are shown here in both fractions and decimals. Here is that data tabulated and plotted. Again, it looks like we could lay this blue curve directly over the top of the one we just saw. However, notice the x values range from -4 to +5, and the maximum y value is 243. Ignoring those numbers, the position of the y-axis itself makes it appear as though the blue curve has shifted leftward by 5 units. This brings us back to translations of a function. A leftward translation is f of x plus h. Using laws of exponents, we see that this is equivalent to a dilation, a stretching of the function in the vertical direction. 3 to the x plus 5 is the same as 243 times 3 to the x. That is shown here. The x values range from -4 to +5, as seen in the second graph. However, the y values are now the same as the graph before that. 59,049 is the maximum value on the vertical axis. Hopefully you now have a visual sense for why translating an exponential function is equivalent to dilating it. In general, that can be expressed in the form seen here. Any base b raised to x plus a constant d can be rewritten using laws of exponents. A number b raised to another constant d is simply a constant. We can label it a. That's enough for this lesson. Stay tuned for the next one, in which we will pick up where we left off. Feel free to ask questions in the comment section below. Thanks for watching. I look forward to seeing you again.